Okay, so the example that we'll do first is an example where it's the most basic example that I can think of, which is if you just have a point charge, just a little tiny dot of charge, and you put it into space someplace. Could you use Gauss's law to figure out something about that point charge? And the answer is yes. And the thing that you can get from Gauss's law is that you can actually derive an expression for the electric field from this picture. Okay? So I'm going to draw here a plus Q, and I'll make it a big Q. And that's going to be my point charge. Okay, so that's that. And my goal is going to be to derive E as a function of lowercase r, which is going to be the distance that I travel from that point charge. It's a radius, right? A radial distance. Okay. So that's my deal. So, okay. So what you want to do here, so this is a case, this is highly symmetric, right? So we're going to use Gauss's law, and we're going to try to get this result. So Gauss's law, our strategy here is going to be the following. We want to pick a Gaussian surface. We want to pick a GS, Gaussian surface, that has the same symmetry as the electric field. Okay? We want to pick a Gaussian surface that has the same symmetry as the electric field. And if we can do that, we're going to get two benefits from it. The benefits are going to be, one, is that the dot product of E dot A is always going to give us kind of the cosine of 0 degrees, which is nice because the cosine of 0 is 1. So that's one advantage. And the second advantage would be that E would have a constant magnitude. If we can do this. If we can pick a Gaussian surface that matches the symmetry of the field. Okay? So these are advantages here, right? Those are the pros. Now, to do this, you have to have a little bit of advanced knowledge of what the electric field is going to look like, right? And you have to have some physics intuition. Now, we know that the electric field that surrounds a point charge looks like spokes on a wheel, at least in 2 dimensions, right? So the electric field is kind of shooting off that way, right? And that way, etc. So the electric field has kind of what we would call this like spherical symmetry, because no matter how you turn that charge around, the electric field is still going to kind of look the same. So for that reason, we are going to select a Gaussian surface that is a sphere. So this is going to be a spherical Gaussian surface. Now, I can't draw a sphere right on this page, so I'm just going to give you a cross-section, which is a circle. So we're going to pretend that that's actually a bubble that goes around this charge. Okay? All right, and if I do that, the wonderful thing about this is that if I look at any little patch, let me shade this in up here. If I take a little patch of that sphere, that patch is going to have an area vector, dA, which points radially outwards. So my area vector, my dA, is going to point directly away from the center of the circle. That's the same direction that the electric field has. You get the deal there? So if my dA vector and my E vector are parallel to each other, then their dot product is going to be very simple because the angle between them is 0 degrees. And anywhere I go around on this surface, I'm always going to be at the same radius r, so the strength of the electric field should be the same no matter where I am. So that's how I'm getting my two benefits from this. Okay. So let's write Gauss's law. So that's the full-on calculus version. And now I'm going to take advantage of my Gaussian surface being so nice and symmetrical with the field. And so I'm going to immediately do this. I'm going to take advantage and I'm going to say that, first of all, that's the same thing as E times E times dA, and I remove the dot product. I remove the dot and I remove the vector hats because I don't really need them anymore. I'll just put a note here. That's because, whoops. Sorry, we can leave it off. That's because the cosine of 0 is equal to 1. So my E vector and my dA vector are always the same way. So I can write that. And then the other simplification is I can take that E out of the integral. And I can do that because of my benefit number 2, which is that E has constant magnitude, right? So E is effectively a constant here. So it's not going to change as I find my dAs. So that's the big deal, right there, those two steps. This is where I get my advantages. Thank you. Can you switch the lights off, Sahaj? Other way, just completely off. Thanks, okay. Can you guys see well enough? Okay. All right, well that's what we got. So anyway, that's the left-hand side of Gauss's law. I've simplified it a lot. Let me do one more thing to simplify it. If I think about this, you know what I lost on here is I lost my closed circle here. I need to keep that. So I'm gonna copy that down again. And then over on the right side, I should carry this down. I'm going to put plus Q over epsilon naught. Okay. All right, is everyone with me on this? So setting up is super important, just knowing to do this. All right, now for $100,000, or maybe not, can anyone tell me what the physical meaning of this is? If I do a closed surface integral over a sphere, do you know what that's actually asking me to represent? What am I calculating if I do a closed integral and I add up all the dAs around a three-dimensional sphere? What am I really finding? The surface area of the sphere, yeah. And so without needing any more calculus, I'm just going to say that's going to be 4 pi r squared. And if I forgot that, which I hope you didn't, you can look up the formula on your green sheet, but that's simply the surface area of a sphere. And I can simply substitute that formula for the integral because I know my geometry, okay? Do not confuse this with pi r squared. Do not confuse this with 4/3 pi r cubed, right? Those are different things. You have to know the surface of a sphere is 4 pi r squared. That's pretty important. Okay, that's equal to plus Q over epsilon naught. And we are just about done because now my goal was to find the electric field, and I just have to get the electric field by itself by dividing. And I'm going to group my terms a little bit differently here. I'm going to take the 4 pi and I divide both sides. And I'm going to combine the 4 pi with that epsilon constant and put those all in one thing out in front. And then I'm going to take the r squared that I divided and move that kind of underneath the q, Do you recognize this? It's the electric field formula for a point charge. Because remember, we said that this is none other than kq over r squared. And remember, the substitution is k is equal to 1 over 4 pi epsilon. So that's actually what we get from this. Okay. All right. I know it's not impressive because we already put this out there and we got this from Coulomb's law before. We didn't use calculus, right? So you're probably like, oh my gosh, why do we have to do all this? But it's just showing you the consistency that you can start with Gauss's law and you can apply Gauss's law to something we really get, and something that's simple, and you can get the right answer for it. So we've achieved the goal. The goal was to derive the electric field as a function of some kind of parameter, and we get the result that we probably would have expected to begin with. Okay. All right. If you made a graph of that, let's just do that right underneath here. That graph would be kind of the typical 1 over r squared. So in this case, it's kq over r squared. Right? No big surprises there. So, all right. What about the r? Does it matter how big the r is? Not really. R can be whatever you want. Little r is just the radius of the Gaussian surface. It's totally up to you.